Hello, and welcome to Acoustics Derivations. In this video, we will derive the characteristic impedance of a fluid. First, what is impedance? Well, often in acoustics, we talk about a specific acoustic impedance, which is equal to the pressure over the particle velocity. To find the characteristic impedance of a fluid, we want to find the specific acoustic impedance of a plane wave. So this here is just definitional, but let's consider now a plane wave. So we consider a 1D system. Here's the wave equation in 1D. And we consider that pressure is some arbitrary function f of x minus c naught t. Now, we're only considering here an outgoing wave rather than an incoming wave, or if you're in a 1D plane, waves traveling to the right rather than waves traveling to the left. Okay, and we'll see why at the end. So we want to solve for P over U. And so, well, we need to find what U is. So we consider the momentum equation, the linearized momentum equation, which states that rho naught du dt is equal to negative dp dx if we're only looking at one direction, which we are. So, well, what is dp dx? Is, well, it's f prime of x minus c naught t, where the prime indicates a derivative with respect to the argument. Okay, well, then we can solve for du dt as simply negative 1 over rho naught times, whoops, skipping a step here, times f prime of x minus c naught t, which then we can solve for u, as what I was trying to do, by taking the integral on both sides. With respect to t, I should say. Like that. Okay, well, now to solve this is a pretty easy integral, but let's let q be equal to x minus c naught t. Therefore, dq is equal to negative c naught dt. Therefore, we have u is equal to 1 over rho naught c naught times the integral of f prime q dq, which is a simple integral, is just f of q. My q's are looking a little sloppy there, my apologies, over rho naught c naught, which then we substitute back in is simply f of x minus c naught t over rho naught c naught. Okay, well, we have P and we have U. We have both of those. So we can solve for the specific acoustic impedance of a plane wave, which again is P over U, which turns out to be f of x minus c naught t over f of x minus c naught t over rho naught c naught, which is equal then to just rho naught c naught. And this gets a special name. This is known as the characteristic impedance of the fluid. So the specific acoustic impedance of a plane wave is the characteristic impedance of a fluid. Here, rho naught C naught. Well, all fluids, rho naught C naught, I should say. And you could also write this if you wanted to as rho times A, where A is the adiabatic bulk modulus of the medium, if you're interested in writing it that way. Now, why did we only consider an outgoing wave? Well, let's consider an incoming wave. If we were to do the same analysis, we would find that Z naught is equal to negative rho naught C naught. Well, hold up. For the outgoing wave, it's positive, but for the incoming wave, it's negative. Why? Well, it's because impedances are directionally dependent. If you were to do the same analysis we did with an outgoing wave, an incoming wave, so with this expression, instead of f of x minus c naught t, you use this g of x plus c naught t, you will find that z naught is negative rho naught c naught. Now, the magnitude hasn't changed, but the directionality, one being positive and one being negative, did change. The characteristic impedance, which we will consider to be positive going forward, is an important characterization of a medium, of a fluid. And it is used fairly often in terms of acoustics. The characteristic of a fluid is used quite often. So we've notated it here, we've derived it here, that the characteristic impedance of a fluid is rho naught C naught. That concludes this video. Thank you.